Okay, so let's go back and look at this problem that you had where you have this this coil that's rotating. In fact, I'm going to go ahead and help you out with this problem so you can just write the answer down. But if I have this situation on the left-hand side, which I have here, I is out of the page, B is to the right, and so the I is out of the B is to the right. So the force here is up. And then similarly, you'll find that the force over here is down. Now, as this thing rotates, when this flips over 180 degrees, what you'll find is that the currents are now going in opposite directions. So if I take this and I rotate it around 180 degrees, now where I did have current going in this direction, the current is going to be coming out of the page. And so those forces are going to switch directions, because as it's rotating, the current keeps going in the same direction, but when it rotates, it's going in a different direction with respect to the magnetic field. And that's going to cause a change in the magnetic force. All right, so that's a hurdle if you're trying to develop an electric motor that you really have to take care of. And there are a couple of different ways to take care of it. So let's first look at this. So when the coil is rotated 180 degrees, the force changes direction. And if you don't do anything about that, you'll have this this loop that is rotating, and basically it'll rotate this direction, and then the forces will change direction, and it'll rotate back that direction. And it'll just flip and flop back and forth, all right? Now, in electric motors, you have to change the direction of the current. After each revolution to keep the loop rotating in one direction. And there are a couple of different ways to do this. The first way, and probably the most common way, is to use a type of switch. If you're in the lab, you've used a switch that changes the direction of the current. In the lab, we call this a double pole, double throw switch. And the switch here that we'll use in an electric motor, it operates a little bit differently, but it does the same thing. It just changes the direction of the current. All right. In an electric motor, part of these switches, they have several parts, but these are called brushes. And then they also have something called commutators, but I'll show you a video on that in just a moment. And these are used in DC motors, where DC means direct current. I think we've said this before, but DC is direct current. It just means current that is always in the same direction, always constant. All right. I have a video here, and you can watch this, and it's a pretty good video, but I'm going to show you a different one that's very similar. I'm going to actually show you two. The first one is just a school project. It's like a how to build your own electric motor. If you haven't done this before, it's kind of fun. This woman makes it look really easy, but it's actually not that easy to get it balanced just right. And they sort of gloss over that a little bit. But notice how when they use the Sharpie to insulate part of the wire, that the reason that they're doing that is that so every half revolution that this motor, the current in the motor will turn off, and so it keeps the motor from flopping back and forth, like a fish out of the water. It has the effect of changing the direction of the current every half revolution, but it's not as difficult as doing that. So watch this first video. It's very simple, homemade, DC motor. Now I wanted to show you another clip. This is actually an actual electric motor, and it shows the brushes and how the direction of the current has actually changed. So every half revolution on this electric motor, you'll find that the current actually changes direction, and you can watch that here. Now, the second way to take care of this, apart from using switches, is you can use alternating current, AC electricity, or alternating current. And alternating current, we haven't talked about it very much, but alternating current, if you were to plot out the current versus time, it would look like this. And it would go from a positive current of some value to a negative current to some value. And it will change at a very regular rate. In the United States, it's usually around 60 times per second, or 60 hertz. And this is basically doing what you need to do. You need to change the direction of the current, and that's what's happening here in an alternating current motor. The current is actually changing direction 60 times every second, and you can design a motor that uses that effect. Okay, we've already talked about generators, but just quickly we'll go through them here. The generator works exactly the same way as an electric motor. In an electric motor, you put a current through a wire that sits in a magnetic field, and it exerts a force on that wire. In a generator, you exert a force on a wire that's in a magnetic field, and it generates a current within the wire. So it's the reverse of an electric motor. So let's consider this. Say that I move this wire through this magnetic field. We've already seen this, actually. We can calculate the current that's in it. If we know with what force we apply, it's going to be F equals ILB sine theta. Whatever the force is that we apply to this wire, we can determine what is the current that's generated in that wire. We had a problem like this before. And then also I can determine what is the direction of the current. So this wire is moving through the magnetic field in this direction. So if I use my right-hand rule, F equals ILB sine theta, or actually, excuse me, I'm going to use this. This is basically the same, QVB, right? I'm going to let my fingers go in the direction of V, so my fingers go to the right. They're going to fold towards the magnetic field, or my index finger will fold towards the magnetic field, and then my thumb will give the direction of the force that is felt on the charges that are in the wire. And so the charges will feel a force that is upward. That will generate a current that is up. All right, so the direction of the current in this wire is up. Right? Generator works in the same way as an electric motor, except you provide the force and generate the current, whereas with the electric motor, you provide the current and it generates a force. All electric generating stations, or all electric generators, operate on this principle. They have a big coil of wire sitting in a magnetic field. Something turns that coil of wire, and that causes the coil of wire to, or that causes a current to be created within the coil of wire. This is a wind power video. It's a very short video, but they just describe how this works in a wind turbine. But they're all the same in electric power generators. Some cases you might have a steam turbine where you take water and you heat it either with coal, gas, nuclear power, and then that steam turns a turbine that turns this coil of wire generating electricity. You might also have hydroelectric power, wind power, where you're using other means to turn this coil of wire. But they all work by the same feature. So why don't you watch this? It's just a minute or so, and we'll pick up with the cyclotron next.